We're going to call this one the long version because I'm sure over the next week or two I'm going to do a shorter version that just gets kind of down to the meat and potatoes and shows off the features of this without spending a lot of time taking it apart, which I'm going to do in this one. We're going to unbox, I'm going to test it, we're going to tear it down and look at the inside of it, okay, and go through all the boring stuff that these long teardowns will entail. Let's check it out. So I was out for a bit today. I came home and there's this great big box that weighs about 60 pounds sitting at my door. This is the official unboxing of the Pecron E2000 LFP 2000 watt power station. This is a big brute. It's going to take me a while to get this thing open. I can barely lift this thing. I have to put it on the ground to actually open the box and lift the unit out, because this thing's a brute compared to the last one that we looked at. Be even more impressive. We're going to put this one through its paces and see what it can and can't do. Okay, so I've put the camera up about as high as I can get it in here on the crane, just so that you guys can see this thing coming out of the box. I'm sure this thing's probably double boxed inside here. Got the AC charger in its own box. The accessory pack. Some packing material. So let's get this out of the box. All right, there's the unit out of the box. Out of the main box. We'll unbox this. I'm going to put it up on the other bench, I think. Maybe I'll work on it on this one. We're going to tear it down and test it out, and we're going to charge it up, give it a full charge first. Then I'm going to put it down through the load test. We'll see what we can run with this unit. Looks like we can run quite a bit, actually. If we look at the specs on the back, it's a 25.6 volt, 75 amp hour battery. 1920 watt hours. We have 6 AC outlets. Rated power is 2000 watts, 100 to 120 volts, 50-60 hertz, and that would be market dependent. USB-A has 3 outputs, 5 volts, 2 amps, 10 watts maximum. USB-A quick charge 3.0 has one of those, 5, 9, 12 or 5, 9 or 12 volts, 18 watts maximum. USB-C has 2, can charge 5 volt, 9, 12, 20 volts up to 100 watts. 12 volt output, 10 amps maximum. There's 3 of them. AC adapter input, 42 volts, 15 amps. That's the charger. And DC charging between 12 and 18 volts, 100 watts maximum. 32 to 95 volts, 600 watts maximum. Discharge temperature minus 20 to plus 45 Celsius. There's minus 4 to 113 Fahrenheit. Charging 0 to 45 Celsius, which is 32 to 113 Fahrenheit. Those are the specs. Let's take a look at the front. So on the front panel, here's our outlets. We have 6 AC outlets. So you can power things such as microwave ovens, frying pans, whatever, up to 2000 watts total. 12 to 18 volt DC input, and these are the 32 to 95 volts, 600 watts maximum. This is for charging from solar panels, for example, and the adapter. On this side we've got DC outputs. We've got 2 standard coaxial outputs plus a 12 volt port here, and our USB ports. We've got a 100 watt and a 5 volt. So USB-C, USB-A. This one's a 18 watt USB-C, USB-A, and this other one here is also an 18 watt. This is an 18 watt USB-A. You can see it. Should turn on some more lights. Those are the outputs there. On the other side over here, there's a battery extender, so you can buy a second battery, plug a second battery into it here to extend the capacity. Great big fans on the side here. These are huge, these fans. I can't wait to try this thing out. But first thing I need to do is I need to charge it, because the battery will not be charged. It also has wireless charging to charge your phone up, and to turn it on and off, press and hold the AC button. That will turn on the AC output. Right now we're sitting at a 66% charge. To turn on the DC, and that includes the USB and the wireless charging, you press and hold the DC button. That'll turn on the DC output. So now we've got both of them on. Again, the battery is at 66%. I'm going to charge it fully, and then we're going to load this thing down. We're going to see what I can do to this unit. We'll put a big heavy resistive load, some heaters and so forth on here, and just drag this thing down to maximum power and see what we can do with it. Pull it down, try to get it close to its maximum output. AC charger is in another box, so let's open that one up. Look, it's still factory sealed. Look at the size of the charger. This thing's huge, big power brick. So this one's going to output, it outputs 42 volts at 15 amps. It draws 6.2 amps at 120 volts or 110 volts. So as soon as I plug in the charger, it should automatically start to charge up, and this should turn red, which it did. It's now charging. The display is telling me that it is charging at 540 watts, which means if you have a source that's strong enough, you could also be drawing power. So if I were to turn on the AC, I should be able to turn on the AC as well, and I can draw, as long as I draw less than the charging power, the battery will continue to charge. So if you're charging this from solar, for example, and you had 500 watts of solar generating capacity, or 600 watts of solar, I think it'll charge up to 600, did it say? 600 watts. So if you had 2 solar panels plugged in, and you were able to get the full 600 watts, and you were running something like a TV or something that drew a couple hundred watts, you'd be still putting a net charge into your batteries. As long as your output is going to be less than your input, this could actually operate as a UPS in that sense of the word, because it would be using the DC input and generating AC. Of course, if you were drawing more current or more power from the AC outlets than your charging current, then your battery would continue to discharge. But you could do that too. If your charging it was 600 watts or 546 in this case, and you were drawing 1,000, your net would be a 400 watt discharge on the battery instead of a 1,000 watt discharge on the battery. Anyway, I'm going to turn that off for now. We're going to let this charge up. When it gets to 100% charge, we'll load this down, we'll time it and see how it works. Once I have it discharged, I'm going to take it apart, show you guys the inside of it. Accessory pack. This will be different charging cords for different scenarios. So it's got the good old 12 volt DC charging cord to charge it up in the car. It's got charging cables to connect it to different type of solar panels. It's got 2 of them here, it looks like. Yeah, it's got 2 cables to connect to 2 separate solar panels. It also comes with a rain cover, so if you're using it at a campsite, you can keep the unit dry. Yeah, what is this cover? Looks like this is the cover that you can slip over it. So there's the rain cover. If you're using this camping, for example, and you've got it set up at your campground, you can... That hatch is to access the wireless phone charger. Zipper on the back here too, you can pass stuff into the back. And it's got this front that can open up. That way you can access your ports, turn it on and off, plug your cables in, right? If you're having it at your campground, plug your solar panel into it, and then you can kind of zip it up to keep the rain away from everything. Have all your cables coming out below. That way you can have this thing sitting outside and charging. And yes, the fans aren't going to ventilate very well through here if they're on, but if it's cool outside, obviously that shouldn't be an issue. I don't think this is going to pass the air, but it'll still circulate around there to keep things cool. But that's your rain case if you're using it camping and it's wet. That'll keep it from getting wet and shorting out, because of course these units here, you don't use them out in the rain when it's wet, and it just snaps over the top. So that's what's good with that. If you're camping, normally you'd have it open, but if you needed to cover it up because it's raining, or it could rain, it's nice that it comes with a rain case. I would think that this hatch on the back is probably so you can slide your phone in and set your phone on top here so that you can keep the cover dry, and or keep the unit on to keep it dry, and put your phone here and keep your phone dry while it's wirelessly charging. Anyway, that's a nice touch that they've included a case, a carry case that you can carry everything with, and it all will fit into your camping kit. Put the carry case in here along with your DC charging cables. Close it up, and you're good to go. Okay, now it tells me the charge is complete. It's gone to a green light. Indicator on the front panel showing 5 watts, and it's decreasing. That would just be the power probably that the fan is drawing as it continues to cool the battery pack. It should be shutting down momentarily. Okay, fans are now shutting down, and it's showing 2 watts, so this is charged. Now we can start the discharge. I'm about ready to start the discharge test. Before starting, I've got the scope hooked up so we can do voltage measurement, frequency measurement, and take a look at the sine wave. I'm going to load it down. I'm going to do it with my heat gun and an electric heater, and we should be able to drive this thing to 2,000 watts of power, and we'll see how long it's going to run. Right now under no load it says it's going to run 128 hours. We're not drawing any power. You can see on the meter here 0 watts, 128 hours. AC out is turned on and we're at 100%. If I turn on the DC output, if I were to drop my phone onto the top, my phone starts charging. It's charging at 5 watts, and as you can see, the display is now dropped to 96 hours. 71 hours now. It's going up to the faster charge. 13 watts is what it's going to charge at for the DC output for the wireless charging. So under no load whatsoever, we are sitting at 128.1 volt, 59.75 hertz, and that waveform looks fairly good. Not quite perfect, a little bit of distortion here, not really much, because again, we're not under a load. First load I'll plug in. This is a electric heater, and as you can see now, I'm drawing 1100 watts, 1200 watts right now, and it's telling me it's going to run for 1.2 hours. Again, our voltage still stayed at 127 volts, 59.72, and the waveform is still holding straight and steady here at a good, nice sinus waveform. So as you can see, 783 watts right now is being delivered to the heater, 800 watts now. I'm now going to plug in the heat gun, and we'll crank that up. Now this one can do 1300 watts by itself, so I'll start it out on low and we'll see what our wattage goes to. Now drawing 1400 watts. The voltage is still 124.9, 125 volts, and the waveform also stayed good. I'm going to turn this up to high and see what happens. This should overload it, maybe. Okay, here we are, 2,000 watts. We have not overloaded anything. The run time has gone down to 0.8 hours. I should time this. Let me get my stopwatch going on my phone here, and we'll see how much time we really get. So now I'm running at full load, 2037 watts is what we're drawing. 98% charge. Oh, it's going to get warm in here. With these two heating devices going, it's already like 30 degrees out here today. It's going to get warm. I'll show you guys the waveform. We're still at 126 volts. As you can see, the waveform is pretty much perfect. If I shut the devices off, it really doesn't change much. Now I've shut everything off. So our power consumption is down to 0. Here we are, sitting at 0. We'll turn the heat gun on low power. Low power, 621 watts is what this is drawing, and it will run for 2.5 hours. If I take it up to high power, there we go, 1386 watts. It's rated at 1350 is what this is rated at on full power, as you can see. Showing a little bit higher, but also the voltage is a little bit higher as well. We'll plug the other one back in. Oh, I went into an overload condition because the other one has a higher inrush current. So, I guess I have to reset it. I'll turn it off and turn it back on. Because remember, the other one drew like 1300 watts when it started. But once it gets going, the resistive element, of course, as it heats up, the resistance goes up. So now we can get back up to full power. Both the fans are moving a lot of air to cool the unit down as we're drawing. Pretty much full power, 1927 watts right now, 1924. But we already saw earlier that I was able to draw more than 2,000 watts. And it only went into protection when I tried to fire up. When I was already drawing 1350 and I tried to add another device which, when it starts up, draws around 1400 when it's cold. That put it into overload. Incidentally, this is the other load here, this electric heater, which is rated at 1500 watts. But of course, the power on this goes down as it heats up. A little micro furnace. Canadian-made one, I might add. I was just thinking, let's draw some more power from here. Let's use a 300 watt inverter on the 12 volt, because this is a 12 volt 10 amp. So I can turn this inverter on, and we'll draw some more power. I'm going to plug my plasma TV into this and turn that on. Now, if things couldn't get any more uncomfortable in here because it's already starting to get warm, I'm going to turn on the TV. Plasma TV just came on. I think it's on. Here's the output of the other inverter. As you can see, it's a stepped output. I don't know if my TV is going to even start up on this, to tell you the truth. I guess I'll see what happens here. I don't think my TV is going to start up on that raspy waveform. So I'll plug the TV in here as well and see if I can fire it up on this. Or will I put this into an overload condition? There, the TV's on. Samsung. Let me get some content playing on it. Alright, I've now got the TV going, and this heater, the power inverter, and the heat gun, and I'm going to put something else on here and load this down a bit. Try to draw as much power as we can. I'm going to plug this fan into the 300 watt inverter, and we'll see how much power we can draw when I turn this fan on. It should run under that modified sine wave with no problem. So now I'm drawing 66 watts on the DC inverter, or the DC power cord, as you can see, for the inverter that's running the fan now. I turn the fan on, you can see that I've got the fan running. So right now I've got a heater, a
a heat gun. You can see how hot that thing is running at full power. Heater, heat gun, and plasma TV running off the inverter. I'm drawing 1851 watts. I've got my phone charging with the wireless charging, and I've got the 12 volt plugged into a 12 volt Pro inverter plugged in, and I'm running my fan. And you can see the waveform. Pro watt inverter is not the greatest. It's what they call a modified square wave. This is how most inverters work. I'll plug my test cord into the pure sine wave output from the Pecron battery pack. As you can see, beautiful. 59.74 hertz, 126.6 volts. Peak is 344, because that's how it works, right? That's peak to peak. TV is still going strong. Running now for about almost 25 minutes. I think maybe it has been 25 because it was a minute or so of operation before I actually started the stopwatch. So this is going to read a little bit low, but 24 minutes so far. We're still at a 55% charge, as you can see. Everything's looking great. Now you've got to remember, I'm putting this under an extreme load. The average person buying one of these units is not going to be running it at 2,000 watts. You've got that capability for starting things like refrigerators or cooking something in your microwave oven, which might draw 1,200 or 1,400 watts, depending on the size of your microwave. I'm putting this under full load because I want to see how long it will run, and I want to see what will happen, whether I can make it shut down. And the average person using one of these things is going to get a lot more runtime out of it than I am, because they're not going to be loading it up to full power and keeping it running. You're not going to be running an electric heater on something like this. You're going to be using it to maybe to run a fry pan or something if you're camping, but that's something that's only going to run for, you know, several minutes and then shut off. So this has got a lot of storage on it. I'm quite impressed. But you can tell the size of this thing. This thing weighs like 50 pounds. It's not a lightweight. But so far, I'm pretty damn impressed with this. For a camper or someone living out off grid in a cabin or something like this with a couple of solar panels to charge it up. Wow, this is pretty much, I think, all anybody would need for off-grid living. And you can also add another battery pack to it. You can daisy chain battery packs to increase your capacity. But 2,000 watts, that's a lot of power. I'm running, let's see, I got an electric heater running. I've got a plasma TV running. I've got a heat gun running. And I'm also running a separate inverter, which is drawing 57 watts. That's including the phone that's charging. If I take the phone away, that'll drop a bit, because I have the phone charger going as well. So I mean, we're pretty much loading this entire unit down. 45 minutes and still going, 18%. It says 0.1 hours. Now 4% now. We're almost there. Might make it to 55 minutes. It's actually probably there now, because again it was about a minute and a half to 2 minutes. There we go. Now it's beeping. It's beeping, telling me it's, oh, temperature alert now. We'll shut some stuff down here. I'll shut that off. Draw the power down to 400 watts now. That indicator indicates that the internal temperature is now rising to the point where it's giving me a warning, but there's 2% of the battery life left. Okay, now the temperature alert has gone away because I reduced some of the power that we were drawing. I took it down to 450 watts. And it cooled enough that the temperature warning went away. Let's crank our power back up again. Run this thing right down. Only got 1% left. Let's see it shut down gracefully when it gets to 0. There we go. 55 minutes pretty much. And she shut down because the battery is dead. that's pretty good. So call it 55 minutes from the time I started the timer going here. But remember, I had the one heater running for a couple minutes before I actually started the stopwatch up. So yeah, 55 minutes at full power. The screws are all actually in the back case here. It's got these plastic plugs that I'm going to have to remove to get the screws out. A little more work than I had originally anticipated to get into this unit, but get into it we need to, because we need to see the inside. That's the whole part of a teardown, is to show you guys what's inside. So I'm going to work with this for a bit, get these plugs out, get the screws out, and then we'll take a look inside. Of course, there's more hidden screws under here. You're going to pull off all 4 of these edge caps because there are more screws hidden, probably under all of them. Okay, all the screws out, the unit should pop apart. Of course, there's more screws on the front. I should have figured that they'd have more on the front here. Okay, I should be able to pull the front panel off now, which I can. This is the control panel. We still can't see the rest of it just yet. The rest of this thing is really quite well assembled. I'm still looking for hidden screws. This thing's really well put together. Now look at the board here. Beautiful. This is just the control board. As you see, all the connectors are all glued together so that they won't just pop apart from bumping it around. This would be silicone insulated wires. It's good insulation on here. I'm pretty sure there's probably screws in behind this sticker, because the back is just not wanting to lift off like it should. This should lift off quite easy with all the screws out, but something appears to be holding it together, and I have a sneaking suspicion that there's probably a screw or two right under this sticker. Ah, I'm right. There's actually 3 screws under the sticker. Well, that would explain why I'm having a tough time getting the unit to come apart. We'll just remove the sticker for now, so we can put that back on later. Get these last 3 screws out, and then this unit the back should pop off of it, so that we can get a look at the goodies inside, including the batteries, because I want to see what's in here. As I'm sure you guys want to see what's in here. And I should be able to remove the entire back, which I just did, to reveal the goods. Alright, here's the inside, the circuit board and the battery at the back here. We've got, I guess that's a current monitoring loop there. Current sense, a shunt of some type. Battery is applied up here. We've got inverter, a couple transformers down there. I don't know if you guys can see them or not. I'll try to turn it around, but we've got a couple transformers in here, one on each side. Heat sink with a bunch of transistors on them. One will be the inverter, one will be the sine wave generator for sure. Our DC power coming from the battery pack is here. Again, I don't want to disconnect any of these plugs on the front. I'm just going to leave this hang here for now. We'll take a look at the actual battery itself. We can see the battery and see what type of cells it's got in it. Right from around this side, here are the cylindrical cells that it's got. I can't see exactly how many. There's 1, 2, 3, 4, looks like 5 or 6 rows of them here, and they are they're 48 watt hour, 3.2 volt, 32140 FS dash 48.0 watt hour. So 32140 cells are what is in this one. So those are the cells that make up this unit. We look back at the main circuit board here again, with the camera down at a lower angle. We can see the electronics. It's got cooling fans everywhere. There's a cooling fan. There's 2 cooling fans in here. There's one on each heat sink. Plus there are 2 more exhaust fans. So these cooling fans here are going to direct air directly into the heat sink. It's a chimney type effect. There is temperature monitors on the heat sinks here. That's what these are. So that's a temperature monitor on each of the heat sinks. There's a couple transformers in here. These will be stepping up the power from the 24 volt battery up to the 120 volts output. Actually, it steps it up much higher than that because you've got to generate it from you've got to generate your sine wave. So this is stepping up your power in a DC. So it's a DC to DC converter. It takes the low voltage DC, it converts it to high frequency pulsating DC to go through the switching transformers, which is then rectified into a high voltage DC, and then the other side, the inverters on the other side, take that high voltage DC and turn it into a sine wave is how these work. So you can see with a current shunt here, there's fusing here, there's 3 fuses here, there's 2 more fuses, external fuses on the back here that can be replaced. These are internal fuses inside it. Circuit board looks to be really well built. There's a conformal coating on it, I can feel it. And there are capacitors inside the heatsink here, but they're air cooled. If you look, there's capacitors in here, but there's forced air that's forced down the channel to drain the heat away. So yes, someone's going to say, oh, they're in close proximity to a heat source, and they are, but again, it's forced air. So there's always air blowing over them to drain the heat away. The hot air is going to exit these fins right here. It's not going to so much get around the capacitors because you're going to have air swirling around here, being directed in and then exhausted out through these exhaust fans at the back here. And here's the exhaust fans are back here. There's 2 of them, and they're good sized fans on here. They be about 3-inch computer fans, but they do move a lot of air, as there was a lot of air movement on this unit when it was functional. And these ones here, of course, will cool the batteries as well. There's space between each of the groups of cells for air to circulate around on the inside and underneath it. If you look on the back here, the batteries themselves are actually sitting up off the ground. The bottom cover goes underneath here, so there's a air space under the battery as well for air to circulate. And there's a space between each of the cells. I don't know if that showed up on camera the last time, but there definitely is a space between each of the cells. If I put my spudger in here, you will see that there is an air gap between the cells that air can go through between each of the cells. So you've got cool air coming in through here. The cool air is being drawn up over the board. It's also being drawn into the battery pack and around between the cells to help cool the cells down. As you can see right here, there's a space. You see there, you see there's a space between each of the cells, each of the groups of cells. So you got cooling air that's going to travel through the battery, over the circuit board, and under the battery to cool everything on here when it's charging and discharging. A very good design, in my opinion. A very good design. Circuit board looks to be really well built. I'm not going to tear this thing down really any more than I have because I want to have a functional unit. I don't want to risk damaging anything, damaging any of these little boards or anything. But everything looks to be good. I don't see anything that leaves me concerned. I'm going to reattach the control panel. We don't need to have this off. Let's pop this back in place. The word of the wise, don't take one of these apart if you're expecting it to be covered by warranty, because you have to pop holes in these plugs. They are so tight that you've got to actually drill holes in them to get them out. So that would provide evidence that it's been opened. I was all set to charge this up with my solar panel. The problem is the solar panel input on this is 32 to 95 volts. My solar panel is only a 24 volt maximum solar panel, so it won't charge this at its potential. I can plug the DC input though. This will take 12 to 18 volts. So I'll set my power supply at 18 volts. We'll see how many watts we can get in at 18 volts. I could connect my solar panel to this input, but I just don't have the right cable to do it. So charging at 18 volts, it's drawing
we're waiting for the charger to get going here. We're now drawing 7.2 amps, 105 watts. And it will take, at this rate, like for example, if you were charging it on your car, well, it would take longer because your car's only charging it at a little under 14 volts. But at 18 volts, it's 105 watts, 18 hours. If I dial this down, let's dial it down to 14 volts, which is roughly where your car battery would be with your engine running. It's still drawing just under 7 amps, 7 amps. 78 watts. Would take a full 24 hours to charge off of 12 volts, well, 14 volts. 13.8 typically is your 13.8 to 14.5 is where most car alternators operate. But it still take 25 hours on 18 volts. Take it right up to the maximum here. Goes up to 106 watts of power, and that charge time drops to 18 hours. That's DC charging. Okay, charger's ready to go. Bye. Charger connected. Kicks into charge mode. Now you see this thing's really getting going now. 500 watts is what we're charging up now. This has a 600 watt maximum. That's 600 watts per port. You can run them in parallel, so you can have up to 1200 watts total. Using 2 of these adapters or using 1200 watts from solar, which would charge it in about an hour and a half at 1200 watts. As you can see, it's now charging at 529 watts, 3.5 or 3.3 hours remaining. We're at 7%. If I tap the DC button, it'll show me what my voltage is on the battery as the voltages come up a bit on the batteries. When they were fully discharged, I did measure the voltage at like just over 24 volts, 24.1 or 24.2, somewhere in there. Anyway, the unit's charging now. I'm going to time it and see how long it actually takes, and then we'll pick this up at the end here, confirm how long it took to charge. Thing I didn't go over on this earlier was the specs, so let's just take a look at the specifications for those of you still hanging around. Well, we all know what this is. We already know what the inputs and outputs are on here. Already showed that over, but here's our specification. So it has a 1920 watt hour capacity. It's a 25.6 volt, 75 amp hour battery. It's a lithium iron phosphate or LiFePO, LiFePO4. So lithium iron phosphate battery will retain 80% charge at its original capacity at 3,500 charge cycles. So you could use this thing every day, and even after 3,500 cycles, it will still retain its 80% of its charge. It's 3.5 to 4 hours standard and 1.5 to 2 hours fast charging. It has overvoltage, overheat, overload, short circuit protection with self-recovery. I think I covered the temperatures before. Weight on this thing, 22 kilograms, 48.5 pounds. Okay, I was pretty good. I guessed it at 50. Felt like 50 when I picked it up. The manual's well laid out. It shows you how to connect your solar panels. These are actually being wired in parallel, actually. It looks like, yeah, these ones are in parallel. 36 volt panel in parallel. 3 36 volt panels in parallel. And then, so total 6 panels. It tells you what not to do. Like, do not wire 3 36 volt panels in series, because that would give you 108 volts, which would damage the unit. You can have 2 36 volt in series plugged into one port and 1 36 volt plugged into the other. That will work. Or you can have 4 of them, where you put 2 36 volt in series into one port, 2 36 volt in series into the other. So it gives you all the different wiring scenarios to connect your solar panel, because a lot of people that would purchase a unit like this
would obviously be using it for solar charging for off-grid use in a cabin or an RV or a camper. Perfect for that. 2 hours and 46 minutes in, 80%. Charging at 548 watts. Let's double up the charging effort. I have another charger here. This one's only a 7 amp 42 volt, but we can plug both of these in. And we can watch the charging go that much higher. Now up to 820 watts. If I had two chargers the same, I could be charging it over 1,000 because we're at 550. So if I had two of these, I could be charging it at 1,100 watts. But I've got the smaller one for the other battery pack. So putting the two of them together, 818 watts of charging power. Our battery voltage is now up to 27.5 volts. 3 hours and 20 minutes. It's still charging at full power, but with no time remaining, it should be shutting down momentary, as it is at 100%. Yeah, I think it's pretty much done. It hasn't gone back into charge again. Watch it make a liar out of me and kick back into charge. But I think it's probably just about fully charged now, or it is fully charged. It's just in the process of cooling down. As you can see, the power consumption is dropping. That would be the fans, and the internal fans are slowing down. And there's not as much airflow now as there was. These are variable speed fans. Anyway, these are great little units. This is the other. I've got two of these. And the thing I like about these Pecrons is the simplicity of use. You don't need to put an app on your phone to control it. Some of them you have to load up an app if you want to put them into surge mode, for example. You have to load an app on your phone. You want to control them. You want to make any parameter changes. You got to do it through an app. This one here couldn't be simpler. You've got a power button to turn on the DC and a power button to turn on the AC. Your outlets, USB, DC, and AC outputs. And your charge input, 12 volt and higher voltage input. Couldn't be simpler. For the hell of it, let's turn on the AC while it's running on the charger and observe what happens when I crank on some power. I'll load this up to 600 watts or so. Charger goes back into charge mode. So it's capable of, now at 170 watts, I'm drawing 600 watts. I was wondering if this will go all the way up. At this rate, it'll run for 3.7 hours with the charger on. If I take this charger off, obviously that time is going to go down. Now it's down to 2.7, 2.6, see? So it will charge and discharge at the same time. I'm curious as to how high this will go. Oh, it's up to 500 watts. There we go. Now it'll run for 10 hours. If I were to plug the other charger in, I'd be completely able to run this heat gun at this temperature setting because I can get 800 watts with the two chargers. So in that respect, this can operate as a full UPS. As long as your load is less than what you are able to put in from the charger, whether it's solar or from the charging brick, you can have up to 1200 watts feeding into this. So you could use this as a UPS and it would function. So if the power goes out, this keeps running. just like that. And it'll run for 2.7 hours. So there you go. It can operate as a UPS. Anyway, thanks for watching.